Allow me to take you on a little journey through inferences and whether they're based on data and are they justified. So first of all, let's go back to the beginning a little bit and talk about deductions. How do you draw conclusions? And it can be in any number of different ways, and they're not equivalent, but they can all be valid. So one is simply logical thought. You observe something, you draw a conclusion. And you can also deduce stuff from literature. You can look up in a number of different papers and draw an overall conclusion of what these papers say. Now you can also draw conclusions from qualitative data, and I want to talk about these things. I also want to talk about issues when you run through experiments. You do experiments and there are design issues with them. And I also want to talk to you about deductions from formal quantitative data. All of these can be perfectly logical, reasonable. They can also, each and every one of them, be totally wrong. And I may mention some other stuff as we go along. So first of all, you're all writing a thesis, and you need to remember that the thesis should tell a consistent story. Logic is important. You should demonstrate in your thesis logical thinking. And you probably also want to draw conclusions from the literature, but do remember that the worst ever justification of a statement in your thesis is that it said so in a paper. Because the literature may very well be wrong, and you need to be darn sure that the equation in the paper is correct. They don't become better by being published. If they're wrong no matter which paper they're in. Now, qualitative data, I mean, as statisticians, we tend to not talk about qualitative anything as actual data. But let's give the social sciences the benefit of the doubt, if you like. Sometimes we can make them quantitative. So in other words, you've sampled a bunch of opinions. If they're a reasonably random sample of the population, then you can sometimes convert these to numbers and you can draw quantitative conclusions of them. Sometimes you can use them as background. So for example, you do a survey of 10, 20 people, ask them general questions on what they think, and then you may know what the most important issues are to put into your actual quantitative survey. And sometimes it's just a part of the story. So in other words, you're interested in doing a certain statistical analysis, but you have background which may even just be a newspaper article. And that's the reason why you set out about this. Sometimes it can be a personal communication. Now, if you have only qualitative information, you usually cannot generalize from it. And you need to be careful with this. You also need to be careful that if you actually do quote someone, that it's actually a correct quote. We've seen many examples in many theses where people cite a certain reference or a purse com and it's an incorrect citation. And if you're in this situation where you quote somebody and that somebody becomes the opponent at your defense, you had better have quoted them correctly. There are certain fundamental issues which you need to be careful with whenever you start drawing conclusions, whenever you start applying logic. And there are simple things like cause and effect. You've all heard the stories that statistical testing in general does not demonstrate what's the cause and what's the effect. And in many cases, you may get data which seem to show a relationship of some sort, but there's actually a third variable which is the real cause for everything. And there are many, many examples of this. Now, there's also an issue of experimental design, and one of my favorites is self-registration. And you can take the example of vitamin E, which people show that if you give vitamin E to somebody who has had a heart attack, you actually reduce the effect of a second heart attack. Now, if you just look at vitamin E in general and people who take vitamin E, you will find that there's a higher probability that people who take vitamin E have a heart attack than those who do not. So what's the real story here? Well, one possible explanation is that the people who take vitamin E, they've actually heard that vitamin E may protect you against a heart attack, and the reason they're worried about a heart attack in the first place is that they're either obese or otherwise susceptible to a heart attack, so you've got a self-registration issue. The people who take vitamin E have a higher probability of a heart attack, and therefore what appears to be a relationship between vitamin E and a heart attack is really just a self-registration issue. And there are similar problems with vitamin D, and we may take that up later under other issues. Vitamin D seems to be linked to depression, so and that seems to be fairly well established. That, in other words, Icelanders take lyse because they tend to lack vitamin D, and the medical profession will therefore suggest to them to take vitamin D in certain doses, and when they lack vitamin D, there are a number of issues that come up. One of them is depression, and whether that's winter depression or otherwise doesn't really matter. The point is that taking a certain amount of vitamin D is good for you if you live in Iceland in winter. The problem is that people seem to think that vitamin D is a cure-all, but it actually can also cause cancer if you take too much of it. We also have an interpretation here, which I want to show you later, which is, well, actually now. Here's an example of data from a breastfeeding example. And here we have a question of cause and effect. There are three groups here. There's the group of women who did not intend to breastfeed, and therefore didn't breastfeed, a total of 90 such cases. And then there's a second group of women who intended to breastfeed, and but they were subsequently split into two because a part of them didn't end up breastfeeding the children for whatever reason, and then the majority actually went ahead and things went according to plan. And then a measurement that was set up was to measure the IQ of the children. And as you can see from the numbers, the IQ of those children who were breastfed appears to be higher than in the other two groups. So what exactly does this mean? So point number one, simply on a data issue, a lot of researchers would skip this group 2A, which are the mothers who wanted to breastfeed, but the breastfeeding failed. This may or may not be justified. And in any case, how would you test the underlying hypothesis? Well, the hypothesis of interest here might be whether breastfeeding affects the IQ of the babies. But this is an example of self-registration again. The mothers who decided to breastfeed in the first place, who wanted to breastfeed in the first place, are probably a totally different group from those who do not intend to breastfeed from the beginning. So there's a confounding element, and I guarantee to you that if you went out and surveyed the background social status of these various ladies, that you would find a much higher level of education among those who decided to breastfeed than among those who did not. And we do know that there's a hereditary component to IQ. So basically, collecting these data in the first place is highly dubious, because for what purpose would you ever collect these data? To show something which you cannot show. But it does give you an excellent example of data which are very hard to interpret. They're intriguing, granted they're very intriguing, but you cannot interpret them on your own. And I haven't even talked about whether the difference is statistically significant or not. I mean, that's a totally different question. It's largely irrelevant because you can't demonstrate anything with it. So here's another self-registration example, several of them. Vitamin E versus heart attack, I already mentioned this, that there may seem to be a relationship, a positive relationship between whether people take vitamin D or not, E or not, and the incidence of heart attacks. Vitamin D versus depression, that's another example. I mentioned that doctors will tend to tell you that it's a good idea to take vitamin D in winter, but it's not at all clear what you get if you just survey the population and ask them, A, do you take vitamin B? B, do you have a tendency for depression? Because it may well be that you'll find a positive link between the two, since those people who have susceptibility towards depression, they usually know about it, they've been to see their doctors, they've checked, and the doctor has told them, please take vitamin B, it may help. And therefore, if you only do this as a self-registration study, you're likely to you're at least in danger of getting totally incorrect results. Now, there used to be a general statement in the public media floating around that told you that vitamin C was good for against the common cold. This came about because a Nobel laureate said in public that he and his family always took vitamin C, and that this helped them against the cold, and they never got cold. Now, of course, these are not data. This is not science. And it doesn't become science even if a Nobel laureate utters the nonsense. The nonsense is still nonsense no matter who says it. So basically, there's very little to show that vitamin C has any effect against common cold. It's one of these things where you usually can say that if you take it, the cold goes away in 7 days. If you don't take it, it goes away in a week. That sort of seems to be the overall effect. None, in other words. But at least it's fairly marginal. I mean, taking vitamin C or eating fruit and vegetables may be good for you in general. That's a different statement. Now, vitamin D suddenly appeared a couple of years ago as a savior against the common cold. So we even have faculty at the University of Iceland standing up and saying, doesn't everybody take vitamin D so they don't get cold in winter? And at least at that time, I couldn't find anything to justify this statement. And it makes you wonder a little bit where people get these things from. Now, the real problem in this is that vitamin D is not like vitamin C. Vitamin C is a water-soluble vitamin. So if you take too much vitamin C, you just end up peeing it away. Vitamin D is a fat-soluble protein. It stays in your body for a while, and so it's not good for you to overdose on vitamin D. And there have been at least 2 experiments where people investigated the effect of vitamin D. It gave large doses of vitamin D to a test group and something else to the placebo or other group. And in one case, they found out afterwards that the vitamin D group had a higher incidence of cancer. And in the other case, they actually had to abandon the experiment because the vitamin D group got too much cancer, got a higher incidence of cancer already halfway through the experiment. So in many of these, there are serious experimental design issues, and you need to check in general the data that you have. Now, of course, if you don't want to check the data, at least talk to your doctor. Your doctor should know the data. Don't just take something. And here's an example of a peer-reviewed article, which you should certainly read rather than just read Facebook on these topics. Now, there are other examples of issues which you need to be careful with. People tend to talk about something being significant, so therefore you need to take it into account. And that's not always true at all. Something may be very highly statistically significant, but not really important. And I could give you several examples from fisheries. For example, if you take a look at logbook data from Icelandic trawlers or any part of the fleet for that matter, you can take things like temperature, and you will find that the average catch per tow is higher at intermediate level temperatures in Icelandic waters than at higher or lower temperatures. So that sounds like an important finding. It's highly significant, but actually the effect is almost none. It's highly significant because you have millions of observations, but the net effect is very, very low. The variability in the trawl-to-trawl or catch or haul-to-haul catch is so great that you would never, as a captain, you would never really notice the difference. But it gives you a nice underlying curve if you take the averages across the millions of observations, averages within each temperature class. Same thing applies to p-values. And this is a related issue, of course. A p-value is a measure of how unlikely it is to get the sort of effect that you measured if the null hypothesis of no effect is true. And this is very useful. It shows you sort of the strength of evidence that you have behind your claim. But the important part is this doesn't tell you anything about whether your result is important or not. It only gives you a measure of significance and nothing else, nothing more, nothing less. So you need to be very careful with the interpretation. The power is in many ways more important. If you have a very large sample size, everything that you look at will be significant. But if you have a low sample size, you need a large effect for it to become significant. And then you see all sorts of things both in the public literature and also in certain even research fields outside the fields where people use a lot of statistics. So people will say that a certain survey is not significant, that a certain sample size is not significant, and none of this stuff makes any sense. There is no such thing as a significant survey. It's not a statistical concept. And a significant sample size is not a statistical concept either. You can ask the question, what sample size do I need to have an 80% chance of rejecting a null hypothesis of a 10% effect? So this is a question which makes sense, and this is how you appropriately use the terms significance and sample size and power. So the answer to these two is just nonsense. We had an example once of somebody who offered to do a survey of size 100, a test survey for beer specifically. So a local brewery had a new type of beer, and somebody came in and said, look, I can check for you to see how popular your beer is, and I'll just take a survey of 100 people and give you the results. Now, we've had general statements from departments at this university who have said any survey of size 100 is completely invalid. And unfortunately, this is complete nonsense. A survey of size 100 has very low statistical power. But if you do the sampling properly, if you do random sampling, then the survey can be perfectly fine. It will show you, for example, the difference between only 10% of the population liking the beer and 90%. It will not show you the difference between 50 and 51%, but it will show you broad outlines. If that's all the brewery wants to find out, is this a complete flop or is it likely to succeed? This may be more than enough, but you need to design it carefully so that these form a random sample of whatever population you're looking at. It may not be the entire population. I mean, it won't be the 5-year-olds. Maybe they're only looking at the teenagers, or maybe they're only looking at the old guys in the old guys pub. So you need to be a little bit careful. And there's another example, which is one of my favorite examples. This one came from the US military, which was trying to buy an autonomous underwater vehicle from a company in Iceland. And they told them go out and do 7 consecutive runs of putting the vehicle into the ocean, send it off on a survey mission, and get it back again. If out of these 7 surveys, none of them fail, you will have successfully demonstrated for us, that the probability of failure is lower than 20%. And you have demonstrated this with 80% confidence. And it turns out when you actually do the algebra that this is perfectly correct. This is a very nice example of small sample statistics, and somebody in the US military had clearly sat there and thought in great detail about how they could specify a test to demonstrate the reliability of these AUVs. Sample size 7 was enough. Now, it gives you certain power and no more than that. Now, here's a different example. This is in fisheries. It's very, very common to fit a model between weight and length to describe weight as a constant times length to a certain power. This is usually fitted using a log-log regression. Now, if you throw that into an ordinary statistics package, it will give you the p-value for beta equal to 0, for testing the hypothesis that beta is equal to 0. Now, unfortunately, in this case, that hypothesis is not interesting. And it's much more interesting in this case to investigate whether beta is equal to 3 or not. Because beta equal to 3 reflects something called isometric growth, whereas beta not equal to 3 is something called allometric growth. So beta equal to 3 means roughly that it grows equally in all directions. Otherwise, the fish is getting fatter as it grows older or something else. In any case, a confidence interval is usually much more interesting to begin with. So if you look at the confidence intervals and the point estimates, you will typically find that with the sorts of data sets that the fishery scientists have, that the power is very significantly different from 3. Very, very low p-values. So you always reject that hypothesis, which is the one maybe of interest. On the other hand, the confidence interval will tell you that the number is very close to 3. So the confidence interval may be 2.98 plus minus 0.001, right? So it's very close to 3, but it's significantly different from 3. And this explains sort of everything in one go, the issue of power and the importance of thinking about what you're doing. And here we have a drug example. You may have an example where you have a difference which is of 0.15, which is clinically important. So that, in other words, could be reflect to a survival rate or a recovery rate or some change or other. And then you can have all sorts of different results for the drug. For example, here are two types of confidence intervals which include 0, so the effect of the drug is not significant. And there are 2 examples here where 0 is not included in the confidence interval, so the effect of the drug is significant. Now, in the second case here, the drug is not significantly different from a placebo, and the effect is very small. It's less than 0.15 either way. In the third example, the effect of the drug is significant, but it's not clinically important. And of course, I've reversed these two. You'll have to forgive me. This is supposed to be 0.05 to 0.1. And then in this first case here, it's not significant, but it might be enormous. The upper bound of the confidence interval is so high that you may simply not have had the power to detect a significant difference, but you cannot show that it's not clinically important. The third case is the result you like. It's statistically significant, it's different from zero, and it's clinically important. The circumstances matter. So the issue with p-values, is that people interpret it in every way under the sun, and all but one of these ways are incorrect. People talk about this, the p-value being the probability that the null hypothesis is correct. Totally wrong. This has nothing to do with the p-value. They say that a low p-value means a good fit. Again, the model may fit the data very, very poorly, yet give you an extremely high low p-value. It only means that if our assumptions are correct, then the probability of getting a value of the statistic as extreme as the one obtained is 2.4%. That's all it means. And usually we will then reject the corresponding null hypothesis, because this is considered an unlikely event. And again, for a p-value of 0.24, that simply means that we are not able to reject the null hypothesis, and the value is 0.24 as getting a test statistic as extreme as this one. So it's not at all impossible. It's not at all highly unlikely to get a value this high, or this extreme rather. It does not mean that you accept the null hypothesis. You should never ever accept the null hypothesis. You only say, I cannot reject the null hypothesis. That's all you say. It does not tell you that the null hypothesis is correct. And this is done in some statistical textbooks, some textbooks that have been used at this university, but it is wrong. If you do work in general in a way where you allow yourself to accept the null hypothesis, then we can easily show that that means that you're not just taking a 5% chance of saying something wrong, which is what you do by rejecting. You're taking up to a 95% probability of uttering totally false statements. You do not want to do this. You do not say, I have shown that the mean is 0. You can use the confidence interval to show that the mean is in a certain interval, but just because you couldn't reject the null hypothesis means only that the confidence interval includes 0. The value of the parameter could be anything else inside the interval. So sometimes it is enough to take a low sample size, small sample size, if you just want to show a big effect. Sometimes it's enough to take a very small sample size, but it all depends on your interpretation. What you want to show and the way you interpret the numbers really makes a big difference. Thank you.